This is Foundations in Pre-Cal 10, Lesson 2.2b, and we're starting about halfway down page 11. Okay, so we're now gonna look at the prime factorization of a perfect square. So perfect squares of whole numbers, it starts 1, 4, 3 squared is 9, 4 squared is 16, 5 squared is 16, 5 squared is 25, sorry, and so on. And every perfect square has two square roots, one positive, one negative, and the positive one we call the principal square root. And so the principal square roots of the ones above, square root of 1 is 1, square root of 4 is 2, square root of 16 is 4, and so on. For this lesson, we're only working with whole numbers, and we're just going to work with the principal square root. So when we say square root, we mean the principal square root in this lesson, just so there's some clarity in the language. All right. We know that we're going to do these factor trees. So if I have 9 and I divide it by 3, I get 3. So I come down here, since 9 equals 3 times 3, the square root of 9 is 3, because the 3 times the 3, but same thing. Okay. For 36, if it's divided by 4, I have 9. And then 4 divided by 4 is 2 times 2, and 9 is 3 times 3. So I come down here and I write out the prime factorization of 36. That's 2 times 2 times 3 times 3. And if I look at this, I can see that I've got a 2 and a 3, and I have another 2 and a 3. So the square root of 36 is what I can do if I rearrange these. Because if I rearrange this, I can write this as 2 times 3 times 2 times 3. And so the square root is this times this. So the square root is 2 times 3, which is 6, which we all know that the square root of 36 is 6. 49, when I factor that, I get 7 times 7. So 49 is 7 times 7, and the square root of 49 is 7. And 64, that's 8 times 8. And 8 is 2 times 4, and this is 2 times 4. This is why I don't like factor trees, because then this is 2 times 2, and this is 2, and this is 2 times 2. See how ugly that got? Let me just do it up here the other way I do it, which is 64 is 2 times 32, which is 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. And all my 2's are in a nice, neat column instead of being, look what I have to do to find these. It's like here and here and here and here, and it's just so much messier when I do it that way. Anyway, the square root of 64, so 664 equals 2 times 2. Somehow I lost a 2 that was there. Oh, I hate it when the computer does that. Times 2 times 2 times 2 times 2. There's 6 of them, right? 1, 2, 3, 4, 5, 6. So to find the square root of this, here I rearranged it so that I had 2 times 3 and 2 times 3. So there's 2 ways I can do this. One is I can just take my whole group and I can divide it into. There's that and there's that. So this equals 8 and this is 8, and they're the same. The other way that I can do it, which is more along the lines of what they're doing here, is if I've got 64 equals 2 times 2 times 2 times 2 times 2 times 2. And what I'm going to do is break them up into pairs. So there's a pair, there's a pair, there's a pair. And we already learned that if everything goes into pairs, I think we learned that, it's a perfect square. So what I'm going to do is I'm going to take one of these, that's this 2. I'm going to take one of these, that's that 2. I'm going to take one of these, which is that 2, and I multiply them together, and I get 8. And that's, I could have also looked at the 36 up there that way as well. There's my pair of 2's, so there's where that 2 comes from, and there's the 3, there's a pair of 3, so I take one of them out, And you can imagine you put one of them into one pile and one of them into the other pile, and then your square root is whatever is in one of the piles, because it'll be the same in both piles. Okay. All right, next page. Here we go. Prime factorization of a perfect square will involve sets of factors which each occur 2 times or a multiple of 2 times. So let's consider the square root of 44,100. So the square root of 44100. I'm going to use my calculator, and it tells me that that's 210. So let's do the example and do this how we use the prime factorization to show that it's a perfect square. So I'm going to factor it, and I get 44100. If I divide that by 2, I get 22020. And if I divide that by 2, I get 11025. And I divide that by, oh, that doesn't divide by 2. What am I doing? I divide that by 3. I know that it divides by 5 because it ends in a 5, but I typically try and divide it by 3 first so that my factors end up all in order, my prime factors. So I'm going to divide that by 3, and that gets me 1225. That doesn't divide by 3. Oh, sorry, it does. Divides by, oh, I missed a number. Sorry. Let's fix this. Okay, 11,025 divided by 3 is 3,675, and that can be divided by 3 to get 1225. That doesn't divide by 3, but it divides by 5 to get me 245, which divides by 5 to get me 49, which is 7 times 7. So if I were to write this out, I write this out as the prime factorization of 44,100. That equals 2 squared times 3 squared times 5 squared times 7 squared. So the square root of 44,100 is going to equal one of these, one of the 3's, one of the 5's, and one of the 7's. And then I take my calculator out and I get 210, which is what I wanted it to be. Yahoo! All right, next example. Use prime factorization to determine if the number is a perfect square. And if the number is a perfect square, state the square root of the number. And I'm going to suggest that you pause the video now. I'll do question A. You can check question A and then pause it again and do question B. All right? So when we do the prime factorization of 1,225, we find that the factors all come in pairs. Therefore, yes, it is a perfect square. And then we take one of each pair and multiply those together. So we get square root of that number is 35. And it's easy enough to check it. Go 35 squared in your calculator. Make sure you get what you were hoping to get. Okay, pause it and do B. 3,042, when you factor it, you end up with one factor that doesn't have a pair. So it is not a perfect square because you can't split all of the factors into 2 equal groups. So it's not a perfect square, right? So let's look at perfect cubes. Perfect cubes, it's actually very similar. It's just that you need to have things in groups of 3 for things to be a perfect cube. So let's do the prime factorization of these perfect cubes. So 27 is 3 times 9, which is 3 times 3. So 27 equals 3 cubed. 216. I'm not going to use the factor tree for that because I just find them not helpful. I like this so much better. So I can divide that by 2 and I get 108. I'm sure you've noticed by now that sometimes I go down the page and sometimes I go across the page. It just depends on what space I have available to me, which one I think is going to work better. 108 divided by 2 is 54. I divide that by 2, I get 27. And 27 divided by 3 is 9, and 9 is 3 times 3. So I can see that 216 equals 2 cubed times 3 cubed. And then 3,375. That doesn't divide by 2, but I can divide it by 3, and I get 1125. If I divide that by 3, I get 375. I divide that by 3, I get 125. Divide that by 5, I get 25, and that equals 5 times 5. So 3325 equals 3 cubed times 5 cubed. Okay. Yeah. So the prime factorization is actually when you write out that a number equals some product of its prime factors. Okay. And this is the prime factorization in exponential form, since I'm using exponents. Okay, so prime factorization of, using this to find which numbers are perfect cubes, it's just the same as doing we did for squares. We just have to look for sets of 3 or groups of every factor needs to come in 3 for something to be a perfect cube. So pause your video. I'm going to do number or letter A, and then you can check your answer. Okay, example 8a, when I factor it into its prime factors, there's a couple of sets of 3, but there's one group of 2s left over. And since not all my factors come in groups of 3, I can't split them into 3 equal groups, and it is not a perfect cube. Pause the video again and do the last example for this lesson. Okay, our last example, we do the prime factorization. We see that all of the prime factors come in sets of 3. That means that it is a perfect cube. And then we can say that the cube root of 970299 equals, and we're going to take 1 from each set. So we're going to take a 3 from the first set of 3s, and a 3 from the second set of 3s, and an 11 from the set of 3 11s, and that equals 99. So the cube root of 970,299 is 99, and you can check that on your calculator too. All right, I hope you did great. Go and do the practice work. Bye.